The floor is yours.
Ivan, you're muted.
Oh, sorry. Sorry. Can you hear me?
Yes, we can hear you now.
Okay, sorry. I muted myself. I'm sorry about that. Hello, everyone. I'm Ivan, and good morning, and good afternoon, and good night. I'm Ivan, and I'm at Princeton. And I want to thank nckh for giving us the opportunity to come together to share our interest machine learning force field. And also, I want to thank Elena and Max for their efforts to organize this workshop. The title of my presentation is From the Potential to the nckh to the Modeling. Let me introduce you about the potential. So the motivation of developing this potential model is we all have known that in molecular dynamics, when we use empirical force field, it's fast, but it's not accurate. And when we perform ab initio molecular dynamics, they are accurate, but it's slow. So it has been many efforts has been paid to use deep neural network to model the potential energy surface in molecular dynamics, and many related works has been talked about in the presentations in the recent days. And we want to develop a model that has both quantum accuracy and the speed of empirical fast force field, so we can and we want to scale linearly with the number of atoms in the system. So in this in 2017 and 2018, the deep potential model has been developed in our group at Princeton, and then many interesting applications has been done with this model. So in the left side of the slide, I'm going to show you some very interesting applications which can be done by the deep potential model. And you can see the quantum accuracy, the very good agreement of the data, the predicted energy with respect to standardized DFT energy. And on the right side, I want to show you the scalability of our model. So you can see from the red line that the DeepMD model scales almost linearly with respect to the number of molecules, while the standard DFT calculations only scales cubically with respect to number of molecules. So their applications are restricted to hundreds of or tens of atoms. And also a very important work of our deep potential model, the phase diagram of water with quantum accuracy has been published. Today, my presentation will be focused on first introduce the construction of the deep potential model, and then I will show you how to use this model. And this is the aim of our hands-on session. And finally, I will briefly introduce the ecosystem of this deep potential model, many related tools and softwares, and a community has been developed, which is called deep modeling. And many people are working in an open source community to make the model and software better. So let me start with the deep potential model. As we all know, the aim of using a deep learning potential energy surface model is to learn the results from some first principle calculations and obtain a model that can predict precisely the energy of a molecular system. So what makes a good model? a good model should preserve the physical constraints of a system. And in our case, we want the model to preserve the following symmetries: translational symmetry, rotational symmetry, and permutational symmetry. So this figure shows how these three symmetries work. The energy of the system should be invariant under translational, rotational, and permutational transformations. And later on, when I introduce the detailed content of the model, I will tell you how these symmetries are satisfied by this deep potential model. And first, I want to show you that after preserving the symmetries, when we train the model, we can lead to lower training errors. We can obtain lower values of loss functions. So on the left side, this is the root mean squared error of the energy during the training process. And you can see that after introducing the permutational symmetry, the root mean square error definitely lowers to another level compared to that without a permutational symmetry. And the same thing happened to the root mean square error force. So we say that after introducing the symmetry preserving into the model, we can recover faithfully the energy and force from DFT calculations. And how can the model do that? With the construction of the model, how can we construct a model that faithfully recover the energy and force of the DFT calculations? Now I want to introduce the model construction of our deep potential model. First things first, the total energy of a molecular system is decomposed into atomic contributions in this model. So we do not include pair contributions and contributions from angle, dihedral, all those kinds of man-body terms do not appear in our model, and we only have atomic contributions. And then this is where the neural network comes in. So we first convert the coordinate of the system into a symmetry preserving descriptor. We do this via a neural network called embedding network. And then we map the descriptor to the atomic energy via a fitting network. So this formula shows how this process works. We first have a set of coordinate, which are a frame of atomic configurations, and then we do some calculations through one neural network, and we obtain a descriptor. Then we use this descriptor to pass through another neural network, and then we obtain the atomic energy. The first neural network to obtain the descriptor is called the embedding neural network, and the second neural network to obtain the atomic energy is called the fitting network. Also, I want to mention here is that the original version of deep potential model only considers the short range contributions of interactions, and we do not include long range interactions here. This consideration works for some cases, and for some other cases, like the calculation of the dielectric constant of water, we must include the long-range interactions. And some work on the long-range corrections of the deep potential model has been done. And also there has been some long-range modules in our deep MD-Kit software. But today's talk, in today's talk, we are only going to focus on the short range version. So in the short range interaction, we have some cutoff length, which above which the interaction decays to 0. And each atom has some neighboring atoms inside the cutoff length. And given this coordinate and given the cutoff length, we can first build an environmental matrix, which is the first step of constructing the model. So we have a set of coordinate, and if we consider one atom and its neighboring atoms, there will be a neighbor plus one atoms, and then we will have, and then we will use the relative coordinates of the atoms, which naturally satisfies the translational invariance. So the translational symmetry has already been satisfied in this step. And then we construct the environmental matrix by using a weighting function, which is 1 over distance inside some smooth cutoff. And outside the smooth cutoff, this function decays to 0 smoothly. So it works just like a window function, and it's a smooth function. And calculating this weighting function gives us the environmental matrix. So it has 4 columns. The first column is just the value of the weighting function. And the next 3 columns are the components on each side, on each direction. So now we obtain an environmental matrix for each atom. And then we introduce the first neural network. It is called embedding neural network, and its role is that we feed the weighting function into this neural network, and then we got the output. The output is the local embedding matrix, which is used to construct the descriptor. So first, in the last step, we have calculated the value of the weighting function, and then we feed it into the neural network, and then we got M1 values, and they compose of a vector. So putting all those M1 putting all those vectors with length M1 together, we have a matrix which is called local embedding matrix. So it has n neighbor rows and M1 columns. M1 columns are the M1 outputs, and the n neighbor rows are because for each neighbor we have a weighting function value. Okay, so now we pass through the embedding network, and it's time to construct our descriptor. The way we construct our descriptor works like this. We have our environmental matrix, which we have constructed in the first step, and also we have our embedding matrix, and we can also take the first M2 columns of our embedding matrix, and then we put all those things into such an equation, which are some operations of matrix multiplication, and then we obtain the descriptor. And the size of this descriptor is M1 times M2, where M1 is the output size of the embedding network, and M2 is a subset of these M2 columns. So given this formula, we can claim that the descriptor intrinsically satisfies rotational invariance. It can be verified by substituting the rotational matrix into this formula, and the descriptor remains invariant under rotational transformation. Sorry. So we can further claim that the energy is invariant under rotational transformation. So after obtaining the descriptor here, we now construct a fitting network to predict the atomic energy. This is a very simple step. We just put our descriptor into neural network. And the input size of the neural network is M1 times M2, which is the size of the descriptor. And the output is a scalar, which is the atomic energy. And now we have the atomic energy and we sum them up to obtain the total energy of the system. In this slide, I'm giving you an overview of how all those things above work to obtain the total energy of a system from the coordinate. And you can see here we have a coordinate, and then we construct the environmental matrix, and we pass it through the embedding network, and we have an embedding matrix. And then we construct the descriptor and put it into the fitting network. And then we have the atomic energy and sum them up to get the total energy. And then we're done. And also, I want to mention a little bit about the structure of the two neural networks. The first neural network is embedding network, and it is a 3-layer MLP. MLP is multi-layer perceptron, and for each layer, it has the number of neutrons which are n to n for n. Where 4n is just a M1, the M1 value, which is the dimension of its output we mentioned, and the dimension of its input is only 1. It is fed with a scalar. So a typical choice in a training process of this embedding network is 25, 50, and 100, which is exactly what we're using in today's example in the following hands-on session. And also there are several sets of parameters for the network. So for the embedding network, we have several different sets of parameters. And how many sets of different parameters do we have? It depends on how we set the training process. If we set the keyword type 1 site to be false, that means the parameter of the embedding network only the parameter of the embedding network depends on which pair it describes. So we have k types of atoms, and then we have k squared types of pairs, and we have k squared sets of parameters. And if we set this keyword to be true, then the number of sets of parameters depend on the number of types of neighboring atoms. And for a fitting network, it is fed with a high dimensional input, which is the descriptor, and then it outputs a scalar value, which is the atomic energy. And it has 3 layers of neurons, with each layer having the same number of neurons. And typically, we have more parameters in the fitting network than the embedding network. So a typical choice is 240, 240, and 240. In the whole model, we also have k sets of parameters for the fitting network, and this set of parameter depends on which type the center atom is. And then I want to mention a little bit about training the model. So when we are training the model, we minimize the loss function. And in our model, the loss function is defined as the sum of contributions from energy, force, and virial. And the contribution of virial is optional. We use a backpropagation process to compute the gradient of the loss function with respect to coordinate. And then we use an optimizer to minimize this loss function. Also, there are some tunable parameters, P epsilon, PF, and P Casei in the definition of loss function. And they're tunable parameters, and they can be set in the input script of our of our DeepMD kit software, and I will show you about the input script later on. So now I finished the first part of introducing the theory of our deep potential model, and then we come to the introduction of the really how we do it. So I first want to say a little bit about the software DeepMD Kit. DeepMD Kit is the software to train and run the model, the potential energy surface. It's totally open source. It's on GitHub, so anyone can contribute it, and any pull request is enthusiastically welcomed. And on last month, on October 14th, we just released its 2.0.3 version. And when it was first born 3 years ago, it supported LAMPs and many interesting applications related to material science and water and ice has been done with LAMPs plus DeepMD Kit. And since this summer, the support to more molecular dynamics engines has been added. So now DeepMD Kit also supports GROMACS and OpenMM. And you're welcome to test those supports and give us feedback. And we also support IPy, which is a specific path integral molecular dynamics package. The workflow of using DeepMD Kit is like that. So we first generate our data, and then we train the model and test the model. And then we use the trained model to run the simulation. So let's first look at how an input script looks like. This is used when we want to train our model after generating the data. So the input scripts are composed of the following parts. First, it has some settings about the embedding network and fitting network, which we have discussed in detail before. In the first graph, the first line to the 15th line, I'm showing you the settings of the embedding network. So you can see some parameters I have discussed before, like the cutoff length and the number of neurons, and also axis neuron. It is exactly M2, which is smaller than M1 I have just mentioned earlier. And also the fitting net, we have the same number of neurons for the 3 layers. And also the training, also we can set the training options like the learning rate, how the learning rate decays. For example, in this task, we are setting the exponential decay of the learning rate, and the learning rate decays for each 5,000 steps. And also we can set the parameters of the loss function. I mentioned there are 3 tunable prefactors of each term in the loss function. And here we are setting the first 2 to be 0.02 and 1,000. And we're ignoring the contribution of virial to the loss function. So we are only setting those things to 0. EFV means energy, force, and virial. And also we specify the data set. So typically we generate our data using VASP and Quantum Espresso. And we are trying to put some training data on the website. So later on, I will show you where to download some very typical training data from our website. And we just specify the directory of the training data in the input script. And then in the last part, we are specifying some training options, like the number of steps of training and where to output the training result and something like that. Okay, and now I will summarize a little bit about a typical workflow of using DeepMD Kit, and then we will go to our hands-on session. So when we are using DeepMD Kit to run a molecular dynamics with the deep potential model, things often work like this. First, we generate the training data. There are two types of ways to generate the training data. The first type is to directly use first principle calculations. I have already mentioned Quantum Espresso and VASP. Quantum Espresso is open source, so perhaps more people have access to Quantum Espresso. And we also have the so-called concurrent learning scheme, which is a highly efficient way of exploring the configurational space. It is called DPGen, which is used to efficiently drive the MD engine to explore the configurational space to generate the training data. The most important point of DPGen is it determines which configuration to label and which configuration not to label, so that you will save a lot of computational resource labeling the data and doing first principle calculations. So the first principle calculations you do in DPGen is the most useful things, the most useful ones, and you don't waste your computational resource. Actually, I was thinking about introducing DPGen when I was preparing for this talk, but finally I found out that the time is too limited. So I will give you some resources on these tutorials after I show you how to use DeepMDKit. And the second step we do is we convert the data format from the first principle calculations. To do that, we have an open source software which is called DPData, and it supports the conversion of data format from various kinds of softwares. And then we train and freeze the model using the input script I have shown you in the last slide. And after training, we just freeze it. So we have a file that stores the parameters of the neural network, which is typically .pb format. And then we test the model to see if our model is well trained, if the if the test error is small enough to be accepted. If we have a satisfying model, then we can compress the model. So dpcompress is a module that compresses the model by tabulating the embedding network so that we save a lot of time in inference, and the compressed model can drive the molecular dynamics process much faster. And then we run the molecular dynamics and compute properties of interest. This is totally the same like what we do in molecular dynamics based on empirical first views. So it's just a use of LAMPs. And now let's go to our hands-on session. And I guess I used half an hour to introduce the theory. So perhaps I will use 20 minutes to do the hands-on session. Do you have any questions before we go to the hands-on session?
Edgar is raising his hand. Go ahead.
Okay, let me go ahead.
So
no, sorry. I meant Edgar has a question, I think.
Okay.
Only if you don't mind. Otherwise, I'll delay it until later, Ivan.
Okay.
So, okay. If I may, what's the idea behind the embedding network? So if I understand correctly, it basically takes the role, if I compare it to something like SOAP gap model or something, it takes the role of the expansion of the atomic density in some suitable basis. Is that correct? So it basically is the step in between atomic coordinates and the calculation of invariance.
Yes. So you mean there is some connection between the embedding network and atomic density expansion?
Yeah, I was wondering whether that's the analogous step in, say, a SOAP gap framework. It's in a SOAP gap framework, you take the coordinates, calculate a density distribution, expand it in a set of basis functions and then start calculating invariance. So I suppose the invariance is something that you calculate after you've translated coordinates into an embedding matrix using the embedding network, right?
Yes, I think that's very reasonable. And embedding network. So yes, it is a way of using the information from the coordinates. Actually, I don't have a lot of knowledge of the atomic density expansion, so perhaps I will see that and then discuss more with you later on.
Okay.
And
so is there maybe I can ask differently then, is there an obvious, or is there an intuitive motivation for this choice of having an embedding network at that point instead of some sort of basis expansion? Because
yeah,
it's tunable to the system at hand at the price of basically having to optimize it during training.
yeah. So I think that the most important thing of constructing this embedding network is that we need to find a way to embed the information of the physical symmetry into the network, and it is a way of doing that. And
but isn't that what you do afterwards when you, for example, do the explicit symmetrization with respect to rotations?
no, we don't explicitly do a symmetrization based on rotation. We were just we were just proving that this construction has already satisfied the rotational symmetry.
Okay, then I need to have another closer look. But thank you.
Okay. Okay, perhaps you can post your questions in Slack, and we would discuss that.
And have another closer look at the actual math involved.
Okay.
But thank you.
Okay. So now let's move on to our hands-on session. And first, I want to say that although many people are using DeepNote in this tutorial, I was not able to figure out how to use the bash commands in DeepNote. So I just uploaded all the materials and my slides into the GitHub. So you can find all the things I use on the, sorry, there's a chat. Okay, thanks Elena. You texted the GitHub link in the chat. So all things I'm using are in this GitHub repo, and you can also find my slides here. So so here are typically the scripts of training and test and doing the molecular simulation and also plotting. So you can just clone this GitHub repo and find what all you need here. And also our data and the trained model is stored in another website called DP Library. It is the place where DP users typically place their models and data. So the use of DP library is quite simple. After going into this website, dplibrary.deepmd.net, you just you need to sign up an account and log in, but it's very simple. And then we, for example, we are using an example of water in this hands-on session. So we just click hydrogen and search. And then all things related to hydrogen are listed here. We have several models related to hydrogen. And for example, water and methane. And in this tutorial, we are using this model. It was published. It was called 2020-10.001, and it is the model that is used in the paper of phase diagram of water. So it has been a model that we use as a daily routine in our group. Oh, there is a chat, sorry. It is also uploaded on DeepNote. Okay, thank you, Elena. And after entering this website, here in data, if we click this, we can download the trained model. It said I need to log in, so I just log in and log in. And let me show you. You can click data, and then you will be able to download a file called frozenmodel.pb. It is the model that is used in the molecular dynamics. So if you just want to use this model to perform your molecular dynamics, that's it. Then the rest of things you need is the LAMMPS input, and you specify the name of this file in the LAMMPS input, and then you're done. It's quite simple. But if you want to see the training data, and if you want to train the data further by yourself, you can download the raw data here by clicking raw data download. And then you will have a tarball, which includes all the things that are used to generate the data and train the model. So I have downloaded this tarball onto my computer, and after opening it, we can see that first there is a VASP input, and there are some ncar files and podcar files that perform first principle calculations. And also we had the training scripts, which are used to train the model. In fact, the most important thing we want to use is this input.json file. And also the generated data are stored in this tarball, so you can also see it. I just uploaded the downloaded PB file onto my cluster, and I put it in the folder of this GitHub repo. Actually, I was thinking about also putting this PB file into the GitHub repo, but it was a little bit large, so I was not able to push it into the GitHub repo. So I apologize that you have to download them separately. And when I come to this folder, we have several things. So this is the folder from the GitHub repo. And you can see we have train data, which is some training data copied from the tarball downloaded from the library, and also the test data, which is some data, some subset of the data in the tarball which are not used in the training process. We use this set of test data to validate our model, to verify if our model is well trained. And then the test folder is the work directory we use to test our model. And the MD folder is the work directory we use to run the molecular dynamics simulations after we obtain the model. So we first enter the train data folder, and then we will find there are several data folders, data init, data iter, and then others. And also I created 3 folders. They are called train, convert, and compress. If you want to train the model yourself, then enter the train folder, and then you will find an input script called input.json, and it looks like this. It's very similar to what I showed you in the slides, and the directory to the training data was properly set. So if you want to train it, you just use the command dp train and input.json. And let me show you my Slurm script. So in the Slurm script, I just use dp train input.json, and I submit it to a GPU node. And let me show you, I submitted. Perhaps I use another folder to not to overwrite my old files. Train.slurm submit. Oops. Shouldn't do that, because the training data is specified properly. So I just dispatch and I submit it. And then I'm running the training process on the GPU node. It takes a little bit time to initialize, but if I show you a successfully initialized task, it looks like this. So this is the output of the training process. And we have several checkpoints during the training process. Also, we have a file called lcurve.out, which stores the learning curve of the training process. And you can see the root mean square error of the training process in this. Actually, typically when training some neural network, we should also have the validation. We should also have the root mean square error on the validation data, but we don't have it in this lcurve.out because we didn't specify the validation data in the input script. And if you want to specify some validation data, you can simply modify the input script, and I highly recommend you to do so. I didn't do that because I'm just doing a very simple demonstration here, and you can also find the learning rate decay in this lcurve.out file. After finishing this training process, I use a simple command called dp freeze to freeze the model from those checkpoints. And after freezing the model, I obtain a new file with the format .pb, which stores the parameters of the neural network. And okay, I just use this dp freeze. Okay, I want to mention that all the commands I'm using today are stored in the commands.sh file. So you can see dp train, input.json, and dp freeze. And if you want to try it yourself, you can simply find all those commands in this file. So I'm freezing this model, and it should be quite quick. Okay. Now you can see that I have an additional file called frozenmodel.pb, which is the model I have trained up to this time point, and it stores the parameters trained up to now. If I want to use this model, I just copy it to other places where I want to use, and for example, compress it and test it. But since I didn't train it for enough time, it is just a very rough model, and I'm not going to use it. I'm going to use the model downloaded from DP library, and it was a well-trained model. One possible issue is that the model we just downloaded was published that year, and it was designed for the first version of DeepMD-Kit, and there are some differences between the first version and the second version, so we cannot use the model for the first version directly. And DeepMD-Kit provides a function called dp-convert-from, which converts the model of the first version to the second version. So we entered another folder called convert, and then we use dp-convert-from, and we can see the help information, and the command looks like this: dp convert from, we specify the input is frozen model.pb, and we specify the output is convert out.pb, and also we can specify the version of the old model, and then we will obtain a converted model which is compatible with the second version of deepmd-kit, and we call it convert out.pb here. This is the model we are going to use to compress, and then we enter the folder compress, and we copy the converted model here, and then we also put the input.json here. I want to mention that the input.json script is also different for deepmd-kit version 1 and version 2. So I just, and the file, the script file you downloaded from the DP library is for version 1. So I just wrote a version 2 compatible input script and provided it for you on GitHub. So you can take a look at it. It is the same as what we used in the training part. And we put these two files, input.json and convert.pb here. And then we use dp compress to compress the model. So the command looks like this: dp compress -i to specify the input model, and -o to specify the output model, and -t to specify the training script. And then after compressing the model, we obtain a file called compressed.pb, which is a compressed version of the neural network model. And this is actually the final model we are going to use to perform our molecular dynamics simulation. And then we come into the test folder where we are going to test our model. And we copy the compressed.pb to this folder, and we simply perform the test command, which is dp test, and this -s specifies the directory to the test data, where and I have put the test data in the folder. So this test folder was copied from the turbo downloaded from DP library, and it is not specified in the training part, so we can use it to test our model. And we specify the output file of the testing process, and some other options, and then we obtain the testing results, which gives in the first column is the test data, and in the second column is the predicted data. So the difference between these two columns of data represent how accurately, how faithfully we recover the DFT data with our neural network. And after obtaining this test data, we can make some plots like this. We plot our test data, test set, and our predict data here, and then we obtain a figure that shows the data points on the diagonal line, which shows a good agreement between the test data and the predicted data. And also, this is for energy, and we can also do it for force. And this model also recovers faithfully the force. Also, I plotted the learning curve in this notebook, and this is the decay of total mean squared error, and this is the decay of learning rate. Since I just ran a very short training process, we didn't see the actual trend, but after we run a simulation which is long enough, we can observe the learning rate to decay exponentially. And after testing the model, we know our model recovers the DFT data faithfully, and then we can perform finally the MD simulation. So we enter the MD folder, and then we can see a little bit about the LAMP input script, which is really a simple script. We just perform an MVT MD simulation, which is in the canonical ensemble, and we compute the radial distribution function of this molecular dynamic simulation, and the system of the system we're simulating is stored here. We are using a very small 192 atom water system to demonstrate it. And the script to run this simulation was also put here, MPI run and LMP. It's very simple. And after running it, we have a file called temp.rdf, which stores the radial distribution function. And I'm plotting it for you here. Since I only ran for 1,000 steps, and I didn't thermalize, it's a very rough curve, but you can see it looks like a radial distribution function. And if you're interested in the science behind it, you can definitely do a longer simulation, and you can calculate a very accurate RDF here. So I'm just introducing. So this is how we use DeepMD-Kit to run a simulation here, if you are interested more advanced things like how to use DPGen to perform the concurrent learning scheme to generate training data, and also if you are interested in enhanced sampling, if you use Plum to perform enhanced sampling, I highly recommend you to go to our GitHub to find another workshop material which describes in detail on how to use DPGen and the combination of DeepMD-Kit and Plum. And also, we several days ago we just we just posted another blog which describes how to use DeepMD-Kit to train a model on graphene. And we provided all of our scripts, both with VASP and Quantum Espresso on our GitHub, and you can find the blog on NVIDIA's website. And we also used NVIDIA's container, NGC container, to deploy the DeepMD-Kit. So you can simply pull the image from the NVIDIA's container and then use it. And you can also find the input scripts, both generating the data, training the model, and running the simulation on this GitHub. So finally, I will briefly talk a little bit about the deep model community. Deep model community is a community of people we gather together due to the development of DeepMD-Kit, and we are aimed at developing good open source softwares so that we can perform molecular simulations better. And on our GitHub repo, we have several good, really fantastic projects, including DeepMD-Kit. We have DPGen, which is used to generate data for DeepMD-Kit. We have DPData, which converts the format of data. And we have DPKS, which learns the Corsham density functional. And also we have Abacus, which is another electronic structure software to generate data for to perform the DFT calculation to generate data for DeepMD-Kit. And also the materials for this workshop is also in this GitHub, and the materials for the graphene tutorial is also in this GitHub. So you can find several very useful resources that really lowers your learning curve of DeepMD in this GitHub. And if you have any questions on setting up the environment or running the simulation or any other interesting questions, you can just email me at ifanl@princeton.edu, and I'm very happy to chat with you about any questions. So in the last slide, I listed the references and the literatures on the deep potential model, the software, and the DPGen, and also the DeepMD kit with high performance computer, which was done on Summit last year. And there are also some very useful things I didn't list, but I'm very happy that I have the opportunity today to share with you my experience with DeepMD kit. And I thank a lot for your patience. And I thank again for Elena and other organizers to give me this opportunity. Thanks a lot for your time. And this is all what I want to talk in this presentation. And thanks a lot.
Thank you very much for your talk, Eva. And I think we have a couple of minutes for questions, including those in the chat. So if anyone has any, do you raise your hands? And meanwhile, Ganesh is asking 2 questions in the chat. The first one is, could you talk a little about the input data format, and is it compatible with ASC?
Okay, I will answer this question first, and then perhaps we go to the next. So the input data format is in the can be 2 types. The first is called raw, which is readable, human readable. The second is MPY, which is a Python format, which is the binary format, and we cannot read. And both of them can be converted from other format using DP data. And on the GitHub website of DP data, we have a list of which type of format it can be used to convert the data to DeepMD kit readable format. So we have VASP, we have LAMMPS, we have Gaussian, we have Quantum Espresso, and ASE, their ASE. I didn't see ASE here, but if you're in need, you can just put it in GitHub, and perhaps we can add the support for you. And so if you're in need, you can tell us your need, and perhaps we can add that support.
Thank you. And then there's a second question about, it says, is the soft embedding added to address physical short-range interactions?
So is the soft embedding added to address physical short-range interaction? Yes. So originally, the very first version of this deep potential model was not. There was not such soft embedding. There was not this smoothing function. It just jumped to 0 at the cutoff length, and there is some unphysical phenomena. And if you run a simulation with that kind of model, in the micro-canonical ensemble, you even see that the energy is not conserved. So this is the reason why the soft embedding, the smooth function must be added. Did that answer your question?
Yes, thank you.
Yeah, thanks.
So can I also ask a question? Or
okay.
sorry if there are other questions, Elena. I think we can take
I
them.
don't see anyone else at the moment, so go
So
ahead.
I don't know whether this has been addressed because I was involved in some teaching, so I just came back. But I'm just curious, I mean, about, can you shed some more light on the descriptor that is used? Because my impression is that it is related to the Beller-Pinello style descriptor in the sense it's related to symmetry functions. It's also a three-body correlation function. Do you think you can shed some more light on what descriptor is used here?
Shed some light on
In the
some
sense, just
three-body.
describe a detail. Sorry, describe what descriptor you're using.
You mean using describe some detail of the descriptor here, or the descriptor here? So I think I have described a lot about the descriptors in this presentation. The descriptor is, I think the most important formula is this. All the things in the definition of descriptor are well defined. We have the embedding matrix. So G is the embedding matrix, G1 is a full embedding matrix, and GI2 is a subset of the embedding matrix. And R tilde is the environmental matrix, which is a function of coordinates. So it is fully well defined, I think. And actually, one thing that can vary in this definition is how we use the environmental matrix. We can use the full environmental matrix, and if you use that in our input script, it is called. Sorry. Need to show you. Input.json. So if I use the full environmental matrix, which has 4 columns here, if I use all of this matrix in this place, this model is the type of this descriptor is called SE-E2A, and we call it A because it has all the 4 columns of this environmental matrix, including the last 3 lines. So it can include the angular information. And if I use the descriptor, which is called SE-E2R, if it is SE-E2R rather than SE-E2A, we are only using the first column of this environmental matrix, and we ignore the last 3 columns. And since the first column only includes the radio information, we call it R. And and I think there is also a type called SE3.
I see.
Yeah, it is much more complicated, and the R tilde matrix is much larger than this, and if you are interested in it, that perhaps we can discuss more in detail later on.
Yeah, I think if you can share the link to this paper, that would be great, because I also received some messages from people asking what the reference was for this. So I think then we can have a look. Yeah.
Okay.
Yeah, but not now. I think you can do it later on. Yeah.
Okay.
Maybe other people can ask questions, but thanks a lot.
Good.
Yeah.
Thanks a lot. Thanks for your question. More questions?
Yeah, there's a question from Ivan. Do you want to go ahead, or should I read it?
I want to go ahead. So thanks for the great talk first. Enjoyed your talk. So I want to ask whether you compared your machine learning model to the other machine learning model, for example, GAP MTP and NNP in terms of performance. So shortly speaking, how fast is your model?
You mean the speed of our model? Yeah. I can provide you with some data on V100 GPU card. If we want to compute a water system, which is of the size of 10,000 atoms, we can compute so let me see. We can compute for each second 40 steps, and we use for example, we use the time step of 0.5 femtoseconds. So let me show you. So 0.5 femtoseconds for a step, and 40 steps for a second, and 60 seconds for a minute, and 60 minutes for an hour, and 24 hours for a day. And we convert femtosecond to, for example, picosecond. And that should be, and we then further convert to nanosecond. That should be 1.7 nanosecond for a day. So almost 2 nanoseconds a day.
1.7 nanosecond, okay, for a day.
Yeah,
Okay.
and it's a large system. It's for 10,000 atoms.
It's for 10. Wow.
Yeah, and only one card.
Okay. I suppose I will ask the rest of the questions in the chat because I have many questions.
Welcome for further questions.
Okay, thank you.
Okay.